Good morning, everyone. Thanks for joining us today at a bright and early hour. I am Robin King. I work at Efficiency Vermont, and I'm helping to host this webinar today. Just a few housekeeping items before we get started. Be sure to mute yourselves because we do want to give the floor to our great presenters. You are welcome to ask questions. We just ask that if there are folks speaking, that you have your questions be presented in the chat. There will be pauses and breaks in the presentation so that you can ask questions live if you want to come off camera and if you want to come off mute. So there will be plenty of space for you to kind of verbally ask your questions. But if you have like a burning question, someone speaking, just post it in the chat and we'll get right back to you. With that, I'm going to turn it over to our presenters to introduce themselves. And I will ask Tim to go first.
Good morning, everybody. I'm Tim Yando. I work here at Efficiency Vermont as a program manager in our residential new construction program and also our program for low-income Vermonters, our energy efficiency program there. I've been here for about a year. I was with the Weatherization Service before that, and before that, I was a home builder for close to 20 years. Putting this together has actually been a great kind of review of where we are with building assemblies. So happy to be here, and I'm going to let Karen introduce herself.
Thanks, Tim. I'm Karen Bushy. I'm a senior engineering consultant. I've been with Efficiency Vermont for about almost 8 years now. I'm working mostly in residential, single family and multifamily, but also branching into commercial a bit. And I have a background in architecture. And I'll turn it back over to Tim to kick us off.
Yeah.
And one more thing before Tim starts. I put this in the chat, but please do be sure to provide your AAA certification numbers, either in the chat or by emailing Bryn Oakleaf. Her email address is in the chat because we do want to be able to report your credits for attending the session today. All right, apologies, back over to you, Tim.
Yep, thanks, Robin. And as Robin said, we will take periodic breaks if you want to come off mute and ask questions along the way. And hopefully we've left plenty of time at the end too for questions and discussion. I just wanted to also let you all know that this presentation is part of a larger series of presentations that we're going to be offering for the course of the year between now and when Better Buildings happens in April, and primarily to continue to talk about safe building assemblies, both residential and commercial, particularly how those assemblies relate to upcoming changes in the building code, which will be taking effect next year. So this is just one opportunity that's come up, and there'll be future ones that will go into even more detail about cost-effective, safe, and durable wall assemblies as we go forward. Let's see. I guess that's it. If you want to go to the first slide, Karen, we're gonna just start out by just going through basic principles of wall assemblies and some building science. I'm going to try to cruise through that part so that then Karen can actually get into looking at actual wall assemblies out there in the field, which I hope will also spur some good discussion. Next slide. But before we start, we just wanted to find out who you are out there. So if you log into the link that's in the chat, you can let us know who you are, or you can put that in the chat if you want to, if you're not able to connect with the link. We're just curious to know who's joining us for this presentation. Okay, next slide. Okay, just a few abbreviations and acronyms that you'll see during this presentation. Hopefully you're all familiar with it, but we tend to all speak in acronyms here at Efficiency Vermont, we're terribly guilty of that. So if there is something that's not on this list, or you come up and are like, what is that? Please, again, ask. So these are just some typical ones that we will use during this presentation. Okay, next slide. So let's talk a little bit about where we were, where we've been, and where we are today. So, back in the good old days of home construction, really before we had all the different types of insulation and knew as much as we did about building science, we would build a home, put what we could in the walls and in the roof, but generally those homes were not very energy efficient, pretty leaky from an air tightness standpoint, and would tend to have all kinds of issues. They were hard to keep warm, hard to keep cool. I guess on the bright side, all that air movement did allow for the control of vapor. It did allow for walls to dry out if they did get wet inside, because usually they could breathe to the inside and outside, and we'll talk quite a bit about that. But our increased focus on energy efficiency, healthy indoor air quality, and climate change has really changed everything. And so we're building higher R-value wall and roof assemblies and foundation assemblies, greater air tightness, which is increasing our need for vapor control and ventilation. Okay, next slide. So this is sort of our typical wall assembly, right? That we've been doing, I think in general, for quite a while, a 2x6 wall with drywall on the inside, and then a vapor retarder, and then some type of insulation, typically fiberglass bats or cellulose or rock wool more recently, then sheathing, and then some type of weather resistant barrier, Tyvek, Typar, and then some type of cladding on the outside. And for the most part, this wall assembly has worked, but it has its limitations in that it's not a very high R value, sometimes difficult to air seal, and difficult to reach the kinds of R values that you're looking for at the juncture of the roof and the top of the walls, because the rafters come right down to the top plates. So we're having to really look at how can we build higher R value walls that are durable, that are going to last a long time, that are going to have no vapor problems or moisture problems, and reach the kinds of energy efficiency goals that we're after. Okay, next slide. So here's these are the four main control layer components of good assemblies. So you have your air control layer. So this is what allows for or blocks air from flowing. Air is a huge component. The tighter the house you have, the easier it's going to be to control vapor and also maximize the effectiveness of our insulation. Obviously, temperature control, that's the insulation, keeping the house warm and cool. Vapor control, which is integrated into the assemblies, both the sheathing, the vapor barriers and vapor retarders that we use on the inside that are required by code, and of course, bulk water control. So keeping out water, snow, wind, the sun. So that's our drainage plans, our roofing, our siding, our perimeter drains, etc. So all these components really work together and need to be thought through to really create a really well-functioning, energy efficient, durable, and healthy house. So again, this is sort of our typical wall assembly. This diagram showing the typical movement of air and moisture from the inside of the house. When typically in Vermont with our houses closed up during the colder season, it's going to be warmer inside. So the drive of pressure is going to be from inside, warmer, moisture air, to the outside, cooler, drier air. And so what's called the vapor drive is going to push from the inside through the drywall into the wall cavity and out through the outside. And again, this is sort of what we've been doing, and for the most part, it's worked, but it has potential problems particularly in terms of moisture. So here is just a diagram showing kind of the whole picture of the insulation. This showing exterior foam insulation on the outside of the framed walls, and the cladding that is vented underneath that. And as I was saying earlier, one of the issues here is getting the proper R value in the roof assembly at the tops of the walls, because often it's very shallow there. We'll show some solutions for that going forward. And making sure that you have a continuous air barrier right from under your slab all the way up into the roof. And we'll get into that details of that shortly. Okay, next slide. Okay, so here's our first poll question that we wanted to pose to you. Again, if you're connected to the link, you can answer this question there, otherwise put it in the chat. But we're curious what you worry about the most. If you're a builder, an architect, designer, homeowner, is it keeping water out of the walls, condensation, air leakage, not enough or too much insulation, the cost of wall assemblies, or just in general, or being able to meet code, or something else? So I'll just give you a minute to chime in on that. And I think that those are, again, on that link.
I'm just interrupting. I'm not sure the link is working. If anyone is able to type in the chat, please do that instead. I'm not seeing any responses show up in the forums, so I'm questioning whether people actually have access to it.
Yeah.
Sorry about that.
A raised hand.
Okay.
From Alan. Alan, if you'd like to
Alan, you
come
want to
up,
jump on? You can go to the next slide, Karen. Okay, well, so Alan, if you have a question, put it in the chat, or wait for the next break. Hold on to your question there. Okay, so let's talk a little bit about air control, the air control layer in the house. So air movement is going to happen. You're not going to have a hermetically sealed home, but the leakier that your house is, the more air movement there's going to be, and potentially the more issues there are going to be in the house, particularly with water vapor getting into the wall assemblies, getting up into the roof underneath your roof sheathing. So by creating a airtight wall assembly with very low air leakage, it's much easier to control water vapor inside the house. It optimizes the R value of the insulation in the walls, so controlling heating and cooling, and also through mechanical ventilation, allowing for optimal air quality.
Tim, sorry to interrupt. Alan is off.
Oh, okay, go Alan.
I just wanted to say that it says chat is disabled, so I don't know how many other people are experiencing that. So there's no way we can chat with you guys or give you any feedback, it looks like, but maybe it's just me.
Sorry about that, Alan. I will look into this. Thanks for noting it.
We're having technical difficulties, it sounds like. Thank you for letting us know that. All right, Robin, I'll let you try to tackle that one.
Sounds good.
Yep. Okay, so yeah, so we need to control air movement. Next slide. One of the sources by which air moves through, obviously, is wind, battering our homes on the windward side. Air leaks in, creates pressure gradients on the inside of the house, then pushes out to the outside. Temperature gradients create changes in pressure in various places of the house, the most common of which in the wintertime is what we call stack effect, where you have cooler temperatures in the lower part of the building and higher temperatures in the top, causing the movement of air from the top of the bottom of the house to the top, moving lots of moisture, lots of heat, creating heat loss. And then the third are just mechanical activities. So an exhaust hood in your kitchen, a bathroom fan, a dryer, whatever it is, all of these things will tend to depressurize the house and accentuate any air leakage issues that are in the house. So next slide. So why is it important to build airtight, as we were talking about? So you have fewer drafts, it's more comfortable in the house, it optimizes the performance of the insulation, it makes heating and cooling easier with less equipment, so that the house, or smaller equipment, so you don't need as big a heating or cooling plant, which lowers your energy bills. It also really goes a long way towards managing moisture, and then rot and mold and all those things that can really affect indoor air quality. And as you see in the diagram, moisture primarily moves into walls through air leakage, as opposed to diffusion through like drywall or sheathing, like in massive amounts. So controlling the movement of air, particularly through the walls, is really, really important. And all the different components of the house have to be interconnected. So you should be able to kind of draw a line as you're looking at your plans before you start building a house. You should be able to basically connect all the dots, all the way from under the slab up through the foundation to your above grade walls, up into your roof assembly, and connect all the dots. So your above grade walls, your windows, doors, skylights, foundation walls, everything all have a continuous air barrier. Next slide. And so here's just a picture of an example, a typical example of where sheathing, in this case, it's taped on the outside for the walls, and on the ceiling, you can see that the seams are taped in the ceiling, creating a really nice air barrier. And then also this sheathing will have some vapor retarding qualities as well, obviously, to the outside. So this is a combination of air and vapor control together that's very typical in a wall assembly. Next slide. So again, continuity is really important, and the materials that you're using. So you want your components to be air impermeable. You want it to be continuous, top to bottom, as you see again in the diagram. You want your air barrier to be durable. So it's better to have, stiff, rigid, strong material, as opposed to like relying on house wrap. So sheathing, rigid foam, spray foam with some caveats, since obviously that stuff can be very finicky, and if not applied in ideal conditions, can actually create air gaps or not cure properly. There's air quality issues also potentially. So there's some both pros and cons for using spray foam, thick poly, and then having the right tapes, sealants, and gaskets to take care of all the little details. Next slide. So it's really important to have a plan going in, so you really understand how you're going to construct your air barrier, where it's going to be, and how all the different components go together. This is just showing really quickly. This is 10 mil poly going underneath the slab in a house I built a long time ago. That on the left, it's showing it before the pour. And then afterwards, once we did our exterior walls, that plastic is then taped to the air barrier, which in this case is the zip wall sheathing. So that plastic is taped right to the sheathing with zip tape. Then you can also see the seams of the zip wall and some nice detailing around the windows to make sure that there's no moisture or air leaking through the windows. And Karen's going to go into a lot more detail about that as well. So let's talk about temperature control. Obviously, this is going to be our insulation. We have all kinds of options these days for insulation, some better than others, and they can be used for different applications, from fiberglass bats, cellulose, rock wool, spray foam, foam boards, denim wool, and wood fiber products that are going to be coming, that have been used in Europe for quite some time, that are going to be coming on the market, that are going to give us some new options as well, both in the form of rigid fiber boards and also fluffy stuff that can be blown into walls and attics. And the other thing that's important to keep in mind when you're building a house, and particularly in terms of insulation, is considering the embodied carbon that goes into the insulation materials. Obviously, things like cellulose, which are basically recycled newspaper, is going to have a very low carbon intensity as opposed to something like rock wool or foam board. So this helps to address not just the operational end of the carbon use of a house, but also the embedded carbon in the house. So just wanted to mention that. So again, this typical wall assembly with this, in this case, fiberglass bats going into a 2x6 wall. Hopefully in the future, there'll be some continuous insulation on the outside. We're thinking that this is going to be a requirement of the code, which we'll get into later. Because this is not faced, this will require a vapor retarder on the inside. In most cases, this is going to be, typically 6 mil plastic or some type of other type of vapor barrier. Next slide. Here's this showing dense packed cellulose in a wall assembly. This stuff is great. I happen to like really using this. It really fills up the cavities really well, tends to decrease air movement, has very low carbon intensity, and is very durable. And also it has a kind of a hydrophilic qualities where it can also buffer moisture, both holding it when it needs to and then drying out really nicely. Again, it's really important in your wall assemblies that your walls are able to dry either to the inside, to the outside, or ideally in both directions. Next slide. This one's just showing insulated sheathing that can be used on the outside. This is becoming more common. One of the differences between these two pictures is on the left in this commercial application using this foam board. That is foam board that actually has a higher permeability than the material on the left, which is foil-faced polyisocyanurate, which is basically going to create a vapor wall. So this is going to trap or not allow moisture to move to the outside. And in Vermont, this is important because, again, vapor drive primarily in the wintertime when our houses are closed up goes from the inside to the outside. So keep that in mind when you're choosing materials to insulate your house. Next slide. And I just put this one in here to show the detail at the top of the wall. So here's a roof truss that has what's called a raised heel truss. And what this does is it really allows for more insulation, raised heel truss that allows a greater space for insulation in the roof cavity. And this really helps take care of the problem of there being a very small cavity where the rafters meet the top plate of your walls. So this is a great strategy to use either if you're using a truss or to use some type of a band to set your rafters on to create this raised heel. This is a very effective strategy for taking care of that juncture. And again, you want to make sure you see the red dotted line that you have a nice continuous air barrier. Next slide. Okay, next one. So let's talk about moisture, which we've already talked about some. We'll get into some more details here. So we need to manage everything from bulk water. So that's, rain, snow, water coming around our foundations, and water vapor. It's one of the biggest factors in the durability and longevity of a house. And it's a major issue in terms of what type of indoor air quality you have. When you have high humidity, it encourages mold and mildew growth. It worsens the effects of chemical contaminants, which are kind of ubiquitous in our homes. And it can actually worsen health conditions of the occupants, immune problems, respiratory problems, and so forth. Next slide. So there's basically 3 rules we want to follow. We want to first keep water out, whether it's bulk water, water vapor, keep it out of the walls, keep it out of the roof. If it does get in, it needs to have a way to get out. And then if something in the wall is going to see moisture, you want to keep it above the dew point so it doesn't condense. So that's basically, the 3 basic rules. However, the caveat there is that this can be complicated because based on the conditions inside the house and outside the house, the relative humidity, the temperature, and so forth. So it's not always as straightforward. So one of the things we want to do is to provide the best wall assemblies that are going to address the greatest range of conditions. Next slide. So where does all this moisture come from? Typically in the first year, there's a lot of moisture in the house from just materials, particularly the concrete, but also in the sheathing and the framing and so forth. And so that all needs to dry out, and that takes some time. Obviously, from rain, from snow, and from activity inside the house, which is one of the biggest sources of water vapor. People breathing, taking baths and showers, activities in the kitchen, unvented combustion appliances, and condensation that can happen inside wall and roof assemblies. Next slide. And how does it get around? Well, if obviously bulk water, if it's getting into your walls because your drainage plane is and your flashing details are not as good as they should be. Water vapor, again, carried by air, and can move into your walls. And if the temperature conditions allow for it, not only will your insulation dampen, but it can condense, particularly on the inside of your sheathing. Water can move through capillary action, particularly in the basement walls, and water vapor diffusion to a lesser degree, crossing through solid material like plywood and drywall. Next slide. Let's see. Okay, so I just want to talk just very briefly about condensation. So, warm air carries more water than cold, and if it reaches the dew point, it's going to condense on some surface. So keeping your indoor air from contacting cool surfaces and keeping humidity at reasonable levels, through ventilation and so forth. So one of the reasons this happens, if you go to the next slide, is obviously, let's see, next slide. These are kind of backwards. So on the left, it's just showing, again, in a typical wall assembly, if it's very cold outside and it's warm inside and you have, say, a relative humidity of about 50%, 70 degrees inside, the potential for reaching that dew point on the inside of the sheathing is really quite high. So if you have a lot of movement of moisture through the wall because of air movement, you run the risk of condensation and frost developing on the inside of that sheathing. So one of the remedies for that is to add enough exterior insulation, typically in the form of foam board, so that interior, the inside of that sheathing, stays above the dew point and doesn't get cold enough for vapor to condense on it. But again, this can be a little bit complicated. And if you get it wrong, it can create real problems. This is a typical problem here in a basement where water vapor can't move to the outside through concrete, and there's a vapor barrier on the inside, which shouldn't be there. It's trapping moisture inside the wall and really creating havoc in a house like this. This is not a good situation. And unfortunately, happens too often. Next slide. I'm just gonna note OSB is a very typical building material. It's okay as sheathing and is a vapor retarder, but it does tend to have a lower moisture tolerance. It tends to it can swell, it can retain moisture longer, and it's harder to really get high levels of air tightness with OSB, and this is really shown in high performance homes that are trying to achieve, 1 air change per hour or less, or passive house, which is 0.6 air changes per hour. So OSB can make it difficult. So if you're really looking for air tightness, it's often better to use a higher quality plywood like Zip Wall or CDX ply. It has good moisture resistance, better in nail and screw retention, and so forth. So always keep in mind the materials that you're using in your house course, you need to keep cost in mind. So it's a trade-off. Okay, next slide. I want to leave plenty of room for Karen. Also available now are intelligent vapor retarders. So these are, they come in a whole host of different types of products and costs, but basically these have variable permeability levels. So when it's very high humidity inside the house, it will have a lower permeability so that or I'm sorry, yeah, a lower permeability so that it will not allow for that moisture to move into the wall. During the drier months, it will have much lower permeability, allowing for moisture to move out of the wall. And this can take some of the guesswork out of managing vapor in your home. And again, these are just examples of different types. And this is another type of variable permeability. I think it's pretty self-explanatory. So I'm going to pass this over to Karen, and she's going to talk a little bit about code, both where we are now and where we're headed, and then just talk about different types of assemblies. Thank you.
Yeah, thank you, Tim. Can everybody hear me okay? I'm going to assume yes, unless
I can hear you.
Okay. I'm going to build on the foundation that Tim so expertly laid for us and talk a little bit about what we can expect to see coming up. So one thing that doesn't look like it's going to change are any requirements around vapor retarding, and that's a good thing. Those are pretty established by now. So this is the language that's been in the code for the last several versions, and just some quick definitions just to make sure we're all on the same page. The vapor retarder is any vapor resistant material with a permeance rating of less than 10. And so that requires us to classify those vapor retarders into class 1, 2, and 3. This is all based on information in the International Residential Code, but what we're looking at, and this kind of puts into perspective what Tim was showing us a couple slides ago with the vapor, the variable vapor barriers. So we have 1, which are basically vapor barriers. We have class 2, which are, you know, a wide range of other products that we see like craft face bats. And then class 3 vapor retarders, really, there's a lot of stuff lumped in there. And what we see with the variable perm vapor retarders is that they sort of cycle usually between class 2 and class 3. So we'll keep that in mind as we go looking at some specific examples of walls. And then vapor open, of course, gypsum board, wood fiber board, cellulose, good to keep that in mind. So again, no change, all based on the IRC, International Residential Code. And what you need to just keep in mind while we're looking at all of this is that the code requires a class 1 or 2 vapor retarder on the inside of frame walls. That's something we tend to forget because we're just really dialed into the exact wall assembly that we're looking at, but here it is in the code. So let's just keep that in mind as we go forward. But class 3 vapor retarders are allowed in certain situations. Now, the IRC allows them with basically a high vapor perm exterior. So you're allowing drying to the outside, to the exterior of the wall. And that they categorize fiberboard and gypsum sheathing as in that category of vapor open. Now, Vermont adds onto that plywood and solid wood, which is kind of interesting and helpful for those of us actually needing to build shear walls. And also just noting, I'm hoping all of you are aware, but this has not changed and probably will not be changing, but the R value requirement over a 2x6 cavity filled wall is 11.25 minimum. And that's something to definitely keep in mind, as most of the walls we see are framed with 2x6s. Again, another thing, we're thinking about different categories of wall assemblies. The RB's handbook from 2020 actually has some really helpful wording of this. They put it into 3 categories of different wall types. A vapor open assembly, that's basically allowing, it's airtight, but it's allowing the vapor to dry in both directions. A control layer assembly, which is a lot of what we see with the vapor control at the interior face of the wall and limiting the amount of vapor that gets into the wall in the first place, and then keeping the exterior of the building, of the sheathing warm, so that you minimize the risk of condensation at that surface. The envelope requirements, we're really just going to be talking about above grade walls and roofs right now. There's a lot in there, but there'll also be, as Tim said earlier, lots of additional trainings that will dive deeper into this. One thing to note is that right now it's just the 2023 draft that's available. There is no final code available for us to consult. So these are just our assumptions, and we're hoping that they're pretty accurate, but keep that in mind. There will be different compliance paths, which include package plus points, which is similar to what the 2020 has, U-factor alternative, looking at the U-factors of the assemblies themselves, and then a total UA option, which will look at the U-factor of the assembly as a whole. And as far as we can tell, continuous installation will likely be required in most, potentially all cases. So that's what we're thinking going forward, and that's what we're going to be talking about in this presentation. The ceiling, it doesn't look like there's any big changes, but you can definitely add R value there for additional points. So that probably is going to be one of the lesser cost areas to do that. And the air leakage is the metric is going to be changing to CFM 50 per square foot of building shell or thermal envelope, which is different than how we are used to thinking of it in the residential world with respect to volume or air changes per hour. So this will be a good thing in the end, because it'll help us be able to talk about buildings in an apples to apples manner, just based on their shell, and not having small buildings have a penalty because of their low volume and big buildings have a benefit because of their large volume. So again, assumptions, not confirmed, but the different assembly combinations that are called out in the draft code that we have seen call out these combinations. So as you can see, they all contain some amount of continuous insulation, the minimum being R10, which I'm not 100% sure that's going to end up in it. Yes, the slides will be available after the presentation. I'm not exactly sure how we're going to get them to you, but we will get them to you. And look for this code information to come out probably early-ish next year, but the requirement, it won't be asked for projects to implement it until about 1 year from now. So September 2023, that's the last I heard anyway. Yep. Thank you for those who filled out the poll. It was that link that I sent earlier that unfortunately I originally didn't send to the right people. But it looks like about 4 people filled it out, and we have quite a range here, which is great and to be expected. We have two folks who are in the exterior continuous insulation category. We have one in the double stud wall category, great assembly, and a framed wall with exhalation, so the high R value to the exterior. So I'm just gonna
Karen,
go ahead.
I just realizing in our eagerness to get all this information, we haven't really taken a pause. So maybe let's just pause for a moment to see if there's any outstanding questions that anybody has. Again, either pop them in the chat or come off mute. We'll just take a little breather here.
Now that we figured out how to enable the chat.
That's right. Thank you, Robin.
Thank you.
Okay, doesn't sound like there's any pressing questions.
All right. Yeah, feel free to type any questions that you have in the chat as we go along, or clarification questions as well. All right, so I'm just quickly going to go through kind of like how I talk about walls so that it's helpful as we dive into some of these details. So when I speak about, when we speak about exterior continuous insulation, for example, that's not, always necessarily like completely outside. It's mostly the defining line is the primary condensing surface or the sheathing usually. So oftentimes when we talk about the interior or drying to the interior, it's to the interior of that surface wherever it happens to land in the wall, or to the exterior would be from that primary condensing surface out. Cavity and continuous, again, like when we speak about cavity, we're speaking about the insulation in between the framing. And even though that could officially be any type of insulation, it's primarily fibrous insulation, which I'll talk about in the next slide. And that's just something to keep in mind. Continuous insulation can be rigid board of any sort. It can be the insulation that goes between the studs of a double stud wall, even though there are other elements of the floor that connect it and technically are thermal bridges, but we're considering that continuous, and the code will consider that continuous as well as like Larson trusses or TJIs or those types of exterior framing members in an exhalation type of wall assembly, where the components that are connecting the outside and the inside piece of that framing are a thermal bridge, but a minimal thermal bridge enough to not be considered a thermal bridge. So for all intents and purposes, those are continuous. That's continuous insulation in that cavity. And fibrous versus rigid, again, this is something, you know, when we talk about fibrous, we're talking about fluffy, air permeable installations. When we're talking about rigid, we're talking primarily about air impermeable installations, but there are some installations that kind of bridge the gap between these. For example, a common cavity insulation is spray foam, but yet that's air impermeable, but you're interrupting it with all of your framing. So also something to consider. And a common air impermeable, which we're hoping we'll see more of coming up, are, you know, wood fiber board and rigid mineral wool board. Those are still considered air impermeable as far as I understand it, but I would not use them as an air barrier, where you might use some rigid foam materials as an air barrier. And one solution is not going to fit all. You know, when in doubt, when you have a question about, you know, a certain assembly, I would at first consult the manufacturer's installation instructions, consult the manufacturer, find out in this application what they recommend. That's always kind of our first suggestion to people when they come to us with questions. We're not trying to reinvent the wheel. We're not trying to tell you a different way to build that's not kosher. All right, so I categorized these examples sort of based on where that primary condensing or sheathing layer falls in the wall, right? First, we're going to talk about a couple that meet this exterior continuous insulation definition. So I've just laid out a couple pros and cons for these. You know, note that the code is going to either require something close to R11.25 out minimum outside of the sheathing, or I think it actually said R12 now that I say that, but the IRC bases it on 11.25. Not that you're going to actually end up with that amount. That's probably why the code says R12. And you're, you know, that's the minimum, but if you were to go less than that and follow the code strictly, you're going to need a class 1 or 2 vapor retarder on the inside of that wall. This assembly has been around for a long time. This is the assembly that we were calling the high performance wall assembly when I started working in this field over 20 years ago. So it's been around, it's tried and true. We're now seeing lower embodied carbon materials for the continuous, the example being on the right, which is showing, I believe that's Gutex. It could be a different kind of fiberboard actually, now that I look at it, but this material actually has an embedded water resistive barrier on the outside of it. So doesn't absolutely require another WRB, which is why you see the strapping right on the face of the insulation there. One interesting thing I came across as I was doing a little research for this presentation was this graphic from the Building America Solutions Center. And once we provide you the slides in PDF form, this is actually a clickable link. So you can dive into that a little deeper if you want to, but I realized that I'm starting to see the WRB in different places in exterior continuous insulation walls, and was kind of curious about that. And this actually explains that the location of that WRB, recommending that it's in a different location based on your climate, basically the amount of rain that you expect in your climate area and the wind. So I think they were actually promoting wall section 1, which puts the drainage plane behind the continuous insulation just because it protects it. I have varying opinions about that, but we can go into that another time. This nail-based panel, basically zip-R, or there are other products that meet that as well. I'm putting in the same category as the continuous exterior. The notable difference is that the sheathing is actually on the exterior of that foam panel rather than the interior. So there are a couple differences that you can consider here, but we are considering it in the same category. So if you had less than an R12 panel, if you had the R9 or the R6 panel, then you are going to be required to do a class 1 or 2 vapor retarder on the inside of that. You have less chance of sheathing rot because your sheathing is on the outside of your foam. So that primary condensing layer technically is the foam, although you're not really concerned about condensation on foam, but you have your studs right there too. And those seams of the zip, if they're not perfectly sealed, the air is going to want to go right through those seams, and that's where you're going to start to see the rot and water impact. Other nail-based panels are available. I've seen Hunter panel specified quite a few times. They also do a vented panel for roofs. Not inexpensive, but it is an option. And note that the R12 zip panel does have additional structural requirements. So that is something we're definitely going to be seeing addressed as we go forward with the new requirements. Okay, this category is the one probably most discussed in the building science world. It is the double wall or double stud wall assembly. And basically, I'm categorizing these walls as the ones that have that primary condensing layer on the very outside of the building with no exterior insulation outside of it. I did a little bit more research again, and it's still like the jury's out. Some people love this assembly, some people caution against it. But in the end, the general takeaway that I get for it is that, so even though the sheathing is cold, you need to keep water vapor from contacting that. There are some things that you can do to ensure a more safe wall. And basically it's these 3 things: build it as airtight as possible so that you're limiting any air that's bringing moisture with it. Include a rain screen, so you're promoting drying to the exterior. And a lot of building science experts really promote cellulose as the cavity insulation in that assembly because it can act as a moisture buffer if there is moisture that gets in there. I mean, if there's a huge water leak or anything, it's probably not going to save you, but it can help. So yeah, I honestly, I don't have a big problem with these walls. The condition that it might be an issue is if, for example, like a developer, a production builder decided to start building a double stud wall, and they were building 100 homes a year or something in Vermont. And I think this wall is much less forgiving. So if you build it well, it'll do great. If you're not building it well or you're rushing, then perhaps there might be problems there. Also in this category of the exterior condensing surface is a thermally broken stud wall, because you don't really have an opportunity to put another layer in there very easily. So some examples of this could be, we see Huntington Homes building these like a traditional 2x6 exterior framed structural wall, and then just putting kind of a thermally broken furring strip inside your wall. Granted, with the new requirements that the code is bringing in the next year, that furring strip is going to have to be pretty deep because they're requiring, R10 or R12 of continuous insulation. So we'll see if folks are able to pull that off. The R5 was pretty easy. T-stud could be another option. I haven't yet seen a home around here use these, but I know that they're being used in the Northeast. I think it's a promising option. And this picture here on the lower right was an example of a builder that I'm working with who builds these beautifully thermally broken studs in the walls and the roof. And I highly recommend it if you're a fine craftsperson, but it's a lot of work. So here is what Building Science Corp is proposing as an alternative to what they're calling the riskiness of the double stud wall assembly, where they're sandwiching that sheathing layer in the middle of the wall and building, it's basically very similar to an exhalation type of wall assembly. And I think it's lovely and it sort of hits all the right points, but the question is, how do you build it? I haven't yet seen anyone build this assembly in any, volume. I've seen people try in like one-off situations, and it's usually pretty time intensive. So we also have some other options. This is what we're seeing more often, which is a TJI or a Larson truss type exhalation or exterior insulation cavity. I have some good pictures of this. I think I'll just go right to that. So basically we're seeing, the TJI or the Larson truss be fastened to the exterior of the exterior sheathing. The exterior sheathing, which is this green board in this picture, is the primary air barrier. It's also the vapor retarder, because there is no interior vapor retarder in this project, I believe. Some folks are doing another layer of Intello inside, but if you're doing all of your insulation to the outside of that sheathing, or even most of it, then you really don't need the additional interior vapor retarder. You can actually get rid of it altogether. You can actually get rid of all the interior insulation in that cavity. So that's what I noted here. I guess the optional insulation, or leave it empty as a service chase. And then again, using cellulose to fill that exterior cavity. In this project, they have a gypsum board as the exterior sheet, as the exterior basically enclosure for the insulation. SIP is pretty self-explanatory. We aren't seeing as many of these days. The important things to consider here, this is great because it includes all of your control layers in it, but it's tricky to get the air sealing correct. You have to be really careful about sealing those seams. And I've seen, conditions where they've opened up in, during the life of the building. So it's not very forgiving. It can be tricky to get it right and not as durable. Before I go into these, I'm going to stop and see if there are any questions that I can answer. That was a lot I just went through. Alan says there's an airspace behind the continuous insulation per building America. Doesn't seem logical. Drainage planes exposed to outside, so R value of continuous insulation is not insulating. Yeah, that's exactly my thought, Alan. I've seen this detail done quite a few times, but yeah, it doesn't make a lot of sense to me. I feel like introducing drainage is introducing air, and you don't want to introduce air past that layer. So in the details that I do, I definitely put the water resistive barrier outside, or the drainage plane outside of the continuous insulation, but I don't see that everywhere. And there are quite a few building science experts that detail it the other way. So I just wanted to put that out there as, there's a couple different thoughts on that, and you can dive into that building science article if you want to find out more. Did you want to add something, Tim?
No, I totally agree. It's a little iffy, and I don't really totally understand it. And that's also been an approach that I took in the past, is to put the WRB on the outside.
Anyone else have any questions? All right, feel free to type them in the chat if you got them. I realize we're kind of running out of time. We have this until 9 o'clock, but we wanted to leave lots of time for questions. So I'm going to try to go through this somewhat quickly, even though there's a lot here. So dive into the slides later, please, and ask us questions. We'll have our contact information at the end. So I just wanted to provide this as an option for folks who are super concerned about moisture in their walls. The Passive House offers some guidelines that are kind of considered like the gold standard for moisture or vapor safe wall assemblies. They're very conservative. I would say they're probably, on the very right end of that scale. So I highly recommend diving into this more if you want to be sure that your wall is not in danger. It has some good rule of thumb values here, which you can see. I'm not going to go into those in detail. Just a note, in walls, this is also the case in roofs, but more so in walls. I see it if you're trying to make your primary air barrier and vapor retarder a smart membrane on the interior of your wall, complicated wall, and you don't have a service chase, it's hard to make that continuous. And that's the primary thing that you want for your air barrier. You want it to be continuous. So this is not something I recommend. Okay, we're going to go through some roof examples. We don't have quite as many of those. This is the one that's sort of tried and true. We see the most, definitely the least cost. It's a design thing. I know not everybody wants a flat ceiling. Cathedral ceilings are really nice, but if you're doing a flat ceiling, by far cheapest, easiest, most commonly done is going to be a flat ceiling with either a smart vapor retarder membrane or just air sealing the drywall. Air sealing the drywall, if it's done well, can get you a really tight plane at the ceiling, which is super important. And getting that at a catch right is also important. So here's some quick pictures of, air sealing that's been done after the fact. For us as folks who sometimes inspect these and verify these, it is often hard to ensure that you're getting this kind of air sealing on a project, because usually the way it's done is that the same contractor is doing the air sealing as the insulating, and they'll go up and they'll air seal all the penetrations, then right away they'll go put the cellulose in, so you don't really get a chance to see. But if you do, this is kind of what you want to see. No holes, no light. Another way to do it, which I'm kind of moving a little way away from the continuous sheathing for an air barrier on the ceiling plane. I just feel like it's a lot of material that is cost that could be saved and material that could be saved. Another way to do it is, like I mentioned before, a smart vapor variable membrane. You definitely don't want to put anything on your ceiling like poly or anything that's not going to allow moisture to dry towards the interior of the room. And there's something in the code about that, and I don't have that language, but if you want to know that exact language, please contact me after and I'll look it up. Here's an example that I found in a Fine Home Building article that I just thought was pretty interesting. They are also doing the continuous sheathing as the top air barrier, and then putting the trusses right on top of that. And what that does is it allows this really nice deep chase to run all of the mechanicals and the electrical in that ceiling. So it was just an interesting take on it. I think it will do something funky with the proportions of the house, but that's another question. Some examples of sloped ceilings. This I just pulled right from the 2020 handbook. What that is recommending, and this is also based on the International Residential Code, is a minimum of R25 for continuous insulation outside of sheathing if you're doing a non-vented roof assembly. You can also do that with spray foam if you really want to. This is kind of my new favorite cathedral wall assembly. I actually am building an addition on my house right now that is using this exact assembly. So this is an article from Fine Home Building. You can dig up if you're interested. It's showing an assembly, I think in Massachusetts or New York or somewhere, that has a not as high an R value requirement in the roof. So they're just dense packing 2x12s with a smart vapor, variable perm vapor retarder on the interior of that, which allows drying to the inside, and strap that so you have a service chase to run all of your electrical and don't have to touch your smart variable perm vapor retarder, because it is also your primary air barrier in this case. And then the top layer of that is just Tyvek, your WRB, and you're strapping that to create a ventilation chase. So you have this perfect drying in both directions. You can build this with low embodied carbon materials, pretty simple, you know, has a little complexity there to the vent space, but nothing, you know, mind-blowing. And then what I did in my condition, because I wanted more insulation than just the 2x12, I ended up building down with a thermally broken stud below the rafter. I also was thinking you could do this with a TJI as your rafter. So the picture on the right is the addition that I'm building, and they ended up just using a piece of foam between the two. Probably might be a good idea to get that a little thicker if you can, but you know, there's different ways. They actually didn't really even need to put that foam in there because we had it blown with cellulose, so the cellulose would have just filled the gap. So that's another way to do it. You're literally framing two roofs at that point. And then some of the pictures that the Fine Home Building article had in it. And just a note with those is you want to, if you're using the Intello on the interior surface of your roof, you want that to be as continuous as possible, and you really need to think through all phases of the design with respect to that, and you're putting in any pieces of that membrane that are going to be impossible to add later. You need to think about putting those in while you have the chance. All right, I think I actually made it through. It's 8:35. So here's some links that will be available in the PDF where you can go to for additional information. Some of these I mentioned. Construction instruction is a really neat condensation tool where you can put in the amount of interior insulation, cavity insulation you have, and the amount of continuous exterior insulation you have, and it will tell you if it thinks your wall is safe or not, depending on your climate zone. So it's a pretty cool tool. All right, I think that is it. Let's go to questions.
Yeah, I just wanted to say for those that are not familiar with the Intello, that's just one of the available, we call smart or intelligent membranes that are out there. And what that picture that Karen had up was showing is a piece that was put in place before an interior wall. There it is. Yeah, it was put into place so that it's continuous, and then you can just continue to tape your next piece so it's continuous along your ceiling plane. So those are the kinds of little details that are really important to think through beforehand. So you've got a clear plan, like I was saying earlier, about where both your vapor control layer and your air control layers are going to be.
Yeah, thank you for mentioning that, Tim. I tend to use the word Intello for all.
Yeah, I do too.
All smart vapor barriers, but there's really great products out there, and more every day. There's all of the Sega products, which are amazing. Partel is another one that's on the market locally that's very similar to for the 475 products. Certainteed, as we saw in the slide that Tim showed towards the end of your section, Tim, right, is slightly different range of vapor perm rating, but definitely a good product and a lot less expensive than some of these European membranes.
Yeah, that's kind of right on the edge of being a class 2 and class 3, but it does fit into that category.
Mm-hmm. So if you have questions, feel free to unmute yourself or type it in the chat. But while we're waiting for that, I was thinking maybe I would go back. I was thinking I wouldn't have enough time, so I was blasting through these, but I wanted to say a little bit more about these Passive House guidelines because I didn't get to dwell on them much. But I wanted to point out that, Passive House actually does not really officially allow the double stud wall assembly with the sheathing on the exterior and no continuous insulation outside of that, unless you have like a separate engineered design or a hygrothermal analysis done of it. So that's just interesting to note that they don't feel confident in that type of assembly enough to verify it as a, just off the shelf, okay assembly. They are recommending, they're just following the same requirements as the IRC and the Vermont Residential Building Energy Standard of approximately a rigid to fluffy R value ratio of 0.5. So half of the R value of your cavity insulation, you want at least that to be outside of your sheathing, which falls into roughly the same 11.25 outside of the cavity wall. I used R23 in this example because R21 fiberglass doesn't quite meet that, but the R23 mineral wool bat would meet that. And again, this is just Passive House Institute US's guidelines for what they consider okay, a vapor safe assembly. And then for their roofs, they actually, their guidance, it asks for a minimum. If you have a rigid, some sort of assembly with continuous insulation and cavity insulation, they're asking for at least 50% of the total R value of that assembly to be the rigid insulation or the continuous insulation. So it's interesting, like I've worked on some projects where that number moves as you develop the project, and you have to really pay attention to increasing both of them, not just one, or not just the cavity.
Yep. Paul,
Okay.
Paul, I see your note. Yes, go ahead, and Art, my email and Karen's are at the end of this presentation, which will also get to you. So you'll have our contact information, or you can just pop the question in the chat as well. Yep, there it is. Thanks.
Yeah, Alan, just looking at your question now. So with continuous insulation and a product like Zip R that contains both the insulation and the sheathing, but the sheathing is to the exterior. This is kind of a question that comes up, but we haven't seen a lot of like real world examples or data about it. One that I have seen was in a Habitat for Humanity house, actually. So I'm going back to that.
Yeah.
Oh, I'm not there. Sorry. Anyway, they did have quite a bit of condensation on the backside of the foam itself. So granted, this was under construction. It was not ventilated at the time. So I would say, yes, the foam is the primary condensing surface, but you're not really as worried about that getting wet, which is why people think it's such a safe assembly. But in my mind, your wood is in contact with that, your wood framing. And if that were to happen a lot over time, it would definitely damage your wood structural framing.
And again, you want to be sure that that is going to, if there is actually moisture condensing in there, that's going to have the opportunity to dry out. But that material is less vulnerable, obviously, because it's foam as opposed to wood, to rotting and mold and so forth.
Yeah, and this might be a good time to just mention that interior ventilation is a big piece of this sort of moisture drive question. Exactly how much moisture can be getting into your walls, and how concerned should we be about that? I mean, we tend to take a very conservative approach because we just don't know how folks are going to use the ventilation, or if they're going to have appropriate ventilation in their home. But if the relative humidity of the interior environment is kept at a reasonable between 40 and 60% or so, you have less chance, especially if you have a very airtight envelope. You really have much less risk of there being condensation in your wall.
Yeah, and I think some of our future talks will go into more detail about ventilation in relationship to assemblies.
And another thing, we were looking at getting some feedback on potential future presentations and what you all are looking
absolutely. Yeah.
to see. So please, put that in the chat if you want, or email us with any ideas or suggestions that you have.
I think, Karen, if I saw right, there's a fairly good possibility that balanced ventilation is going to be required in the new code. Again, we're not totally sure about that, or that at least it will be a points option going forward. So also really keep that in mind, and really as best practice, there are some fairly good cost-effective balance systems, air exchange heat recovery systems that you can put in homes now that make such a huge difference in terms of moisture control, indoor air quality, and so forth, and just comfort in general.
Mhm. Yeah, that's a great suggestion, Ellen. We'll definitely note that once we know exactly what the code is requiring, that'll be easier to do. Have a presentation that's more of a dialogue with required wall and roof assemblies.
Yep. And of course, you know, any of you that are listening in that are part of the Efficiency Excellence Network, also feel free to connect with our team of engineering consultants too that can also help you work through the details of your wall assemblies, ventilation, you know, mechanicals, heating systems, and so forth going forward. That's a big part of why we're here, just to help with that, and a big reason why the network is in place now, so we can provide those services to you. There's a wealth of information on this team.
Well, we probably can go ahead and close out, I'm thinking, if we don't have any other questions, and folks can just email us if they have further thoughts.
Yep. Yep. So this is going, as I understand it, it's going to be posted on the Efficiency of Vermont website. And I believe it will be on there today. If you want to
by next week, Tim.
By next week. Okay. Thank you, Robin.
You're welcome.
Yep. And will a link be sent out to participants?
I think we can accommodate that, or if folks want the slides, let us know. I'm sure that we can send them along, but yeah, just let us know how you'd like to receive it. I see slides. Yes, please, from Alan.
Yeah.
Noted.
Yeah. Yeah. I guess the last thing I wanted to say is I know we went through an enormous amount of material and information. So if your head is spinning a little bit, that's okay. My hope is that you've digested, you know, some of this information in a useful way, and stay at it, so that you get to a place, depending on, you know, where you are, whether you're a builder, a designer, architect, homeowner, whatever, so that you really feel like you're beginning to get a grasp on these concepts, because they're so important in terms of, you know, building long-lasting, durable, really energy efficient homes. And also, I want to encourage people to also consider the green aspect to it, particularly the health aspects of materials that are going into your home, which are a big part of indoor air quality. So your finishes, your cabinets, right down to your furniture, which can sometimes contain things that can off-gas and cause problems unbeknownst to you. So to dig into that as well.
Yeah, I just posted also, I reposted Robin's email or message from earlier about providing your AA certification number for credit, in case folks didn't see that early on.
Yeah. All right, so yeah, thanks for those of you who joined us. It was a pleasure presenting this to you, and we're looking forward to doing more in the future.
Yeah, thank you all.
Have a great day, everyone. Thank you.
Bye.